Hello, this is my presentation for Lab 1. For my introduction, the purpose of this lab is to compare object and constant velocity in motion and compare them between observed and predicted model and to analyze any underlying forces that might cause the two data to differ. In this lab, my model will use Newton's second law and compare observed and predicted data to help verify that principles such as zero net force for constant velocities are correctly represented. The preview for this lab, I analyzed the motion of an object and discovered that the rate of change of an object's position varies due to unbalanced net force. As it refers, there's a difference in the observed and predicted data. For my, to go over my initial condition, my calibrated stick will be my M2 13-inch MacBook. For the dimensions will be 0.304 meters width and 0.215 meters length. The object in motion will be a toilet paper in 0.085 kilograms of mass, and it will be mainly measured in the second coordinate system. The second quadrant of the coordinate system, and for my delta t, it will be 0.033 seconds. So here is my experiment. You can see my hand here, and at 0 is my starting point with my calibrated stick in the background at the couch. So there it is. Okay, so here is the video I put in tracker, and this is the data I got, and you can see at 0 time, this is my starting point for x and y value. For my GlowScript, code, so this is my predicted value, I use the average velocity formula, which will later come up to help update the new position as it's being used in the update position formula. So here I'm using the final position minus the initial position divided by the final time minus the initial time. And here are my data based on the graph, the model I just showed you, and negative 1.788 will be the average velocity that we will use for the position update formula. Just to get a better picture of this, here is the code I use with here's the attribute of the toilet paper, here's the starting point, and here is the average velocity in which I calculated with delta t. Here is the position update formula with ball.vel is the average velocity times delta t. So as every time this is being updated, our final position is also being updated every time these values are being iterated. So this is just to help us so the program can generate a new program every time the ball is moving, since we're assuming that the ball is moving in a constant velocity. So okay, so going back to the presentation, here the formula this is the formula I just talked about, I used, and the position update formula is derived from the average velocity formula. You just have to solve for the final displacement. Okay, and next here's the model that's being generated. Okay, so here's more of a side-by-side comparison in an Excel sheet. On the left-hand side, we have the predicted value generated from tracker, sorry, not tracker, GlowScript, and then from the right-hand side is tracker, which is the observed value. You can see there's some slight differences, key differences and similarities, which we'll be discussing here. For the differences, there is an unbalanced net force. The values here are varying by a lot. It's not changing in constant. Here it's changing constantly. You can see like a pattern to the factor, but here it's unpredictable. Even the y value is not, it's varying unconstantly. So that indicates an unbalanced net force, and changing direction, there is a change of direction in the sense that here in the beginning, the object did kind of like bounce here when I drop down the toilet paper. So that causes the change of direction, which already causes the change of net force. So, and of course, constant versus varying rates of change of position that I just talked about, the rates of change are completely different for both models. For similarities, both data are increasing in the same negative x direction, and there's some forces being applied since both are assuming that the object is changing in displacement. And same starting point at 0 time, since there's no constant velocity that's being updated yet for the starting point. To go over the what if, so if our x values were changing in signs, what will change? It will definitely be the vector values. So anything with magnitudes and directions will be changed. The directions will be completely reflected, and graphs such as like the position time graph will be mirrored, velocity time graph will be mirrored vertically, and values such as velocity, acceleration, displacement will now point in a different direction along the x-axis. What will remain the same will be our scalar values, so speed and distance, mass will be the same. That does not affect the magnitude. Overall physical behavior, the physics of the motion won't change, so how the object moves won't change. All of that is just a reference frame. The object will still follow the same path relative to its environment. Another lab question is it possible for us to say how many pushes and pull are being added together to get a zero net force? I would say the answer is no, not possible, because it's not possible to say that, because zero net force can be achieved when all forces are balanced. So forces such as gravity, normal force, and applied force, friction, air resistance are just some examples where forces can act on an object. You will achieve zero net force when all of those forces are balanced or like canceled out, and it equals zero net force. But to say that we can predict how many forces are being acted on just because it has zero net force is impossible, because you can have many possibility of many forces acted together, and it's still possible that all of them can cancel each other out. Of course, that might be unrealistic in the real world, but it's something to be considered. So just from that information alone, I would say it's not possible to say that we can tell how many pushes and pulls are added together, given the information that the net force is zero. Okay, so for the potential error for the lab, I would say it would be inaccurate tracking. In tracker, it's possible that when I pinpoint the object in the graph, I didn't pinpoint it correctly on the axis, so that will give me different data already. The object's motion going back and forth of the camera, that can defeat the purpose of trying to get constant velocity. Dropping the object because it bounced on the table and potentially changing its direction, again, defeats the purpose of having zero net force. Calibrated stick has inaccurate measurements causing inaccurate data. Since calibrated sticks are used as reference point, it's possible that when I convert my MacBook from inches to meters, I didn't convert it correctly, so that would have already influenced my data. And of course, calculation errors when I solve for average velocity, maybe I rounded wrong. There could be rounding errors, so that's something to consider as well. So conclusion, the change in net force causes observed data to cause a velocity displacement variations compared to predicted data. Zero net force can occur when there's a constant velocity or when the object is motionless, but we cannot conclude how many forces are being applied from that information alone. The new position are generated through constant rate of change from the formula we just solved, and is updating through the new update position formula as the object is iterating through delta t times. And the orientation of the axis does not change the vector value of the data, but does not affect the scalar value of the data. So, and also doesn't change the motion of the object.